Hello, my name is Huterer Prats, and today I'm going to be talking about autonomous space-based imaging, in particular reinforcement learning scheduling with imaging downlink trade-offs across different orbital regimes. To jump into the motivation, it stems basically from rapidly growing space awareness challenge, which comes from the number of RSOs, the resident space objects, skyrocketing in the last couple of years, and the ground-based sensors that are used to track these objects not keeping up with that growth, and they cannot keep up with the challenge. Also, in terms of strategic interests, similar to air traffic radars, we want to understand, can we observe all the activity in a particular region in space? And to do that, we need to gain knowledge of the states of the targets, of the target RSOs in the catalog that are of particular interest. The research focus has mostly been on optimizing ground-based task scheduling, but as those capacities are reaching their limits and space-based assets need to be used in conjunction, now we also need to expand research in that field, and that is still in the early phase. In particular, space-based space surveillance requires continuous onboard decision-making, and you're operating under tight pointing, illumination, and spacecraft constraints, which means this is fundamentally a closed-loop autonomy problem, similar to the agile Earth-observing satellite problem, which has been dealt with many times in our lab, where you're keeping a catalog of ground targets. In this case, you're looking at stationary or slow-moving targets where the sequence of targets is quite predictable, and all the targets are below you, where you're either slewing left-right or ahead or back in the ground track. If you then want to convert this to something like a space-to-space surveillance satellite, where you're keeping a catalog of space targets, you're now looking at very fast and slow-moving targets, so there's very quick relative dynamics, and the sequence of targets is quite unpredictable, especially when you consider illumination constraints and line of sights, etc. Also, in this scenario, they can come from all possible directions. They're no longer just below you, but they can be above you, behind you, and on the sides, etc. So, to look at the problem statement, in prior work, we looked at an implementation of LEO to LEO, where we're having a LEO platform trying to image 100 other LEO targets. Now, in this work, we're trying to understand, can a LEO-trained policy maintain performance when applied to a mixed environment? And also, can a multi-objective reward function be structured to incentivize image delivery to the ground? So, in particular, what we want to achieve in this problem is to maximize the fraction of successfully imaged and downlink targets out of all the RSOs in the environment. And to do that, we have these 4 different action types that one can choose: imaging a target, charging the satellite, doing a desat maneuver, or downlinking data to one of these 7 ground stations that is imaged on the right. There's several constraints though. In particular for imaging, there's target visibility and imaging pointing constraints, etc. During the whole simulation, we also want to maintain spacecraft safety for the battery levels, the reaction wheel speeds, and also we need to manage the storage capacity. So if the storage is full, you first need to downlink before you can actually take a new image again. To give a quick background on the simulation setup, where all the details can actually be seen in the paper, but we're looking at 100 RSOs now, which are spread 50, 30, and 20% between LEO, MEO, and GEO. And the episode is around 8 orbits long, which gives it around 150 imaging actions worth of time. So in theory, it has enough time to image all of them, but in practice, as we will see, you don't always have visibility to all of them, or there will not always be mutual visibility throughout the course of 8 orbits, especially when you consider lighting constraints. Similarly, also the simulation architecture, showing exactly what type of control we're using with MRP feedback and how it's implemented, is shown in the paper, and I encourage you to look at those details for that. All this is being simulated in BSKRL, which has 2 fundamental layers. One is Basilisk, which serves as the fast and high fidelity flexible simulation framework, where we do a lot of our research. And we combine that with Gymnasium, which is our reinforcement learning environment interface. So from our agent, we receive an action, we propagate that in our environment Basilisk, and from that we get back a reward and an observation. And we use that to train our agents, and that is done using proximal policy optimization, which is an actor-critic architecture. So all this combined is BSKRL, which has been used not only for this implementation, but also Agile Earth observing implementations and also RSO inspection work. The way it is formulated in this scenario here is we have our Markov decision process, which contains the observation space that first has a set of spacecraft observations, which is the the data storage, the battery, and the momentum of the spacecraft. Then the next set of observations are for each target. We have the elevation angle from the ground, from the horizon, the relative position vector in Hill frame, the current pointing arrow, which is the phi angle. So if you were currently looking at the green target and now decide to look at the orange target, you had this phi angle of initial pointing error. Then we also provide the distance to the target eye as well as the current illumination status. So if you're illuminated only partially, as it's currently the case for the orange target over there, then you don't have a full illumination factor. Also, we give information on the environment where we're looking at the eclipse start and end times that is provided to the agent, as well as the next two upcoming opening and closing windows for ground stations. The actions, as I mentioned before, you actually get 10 different imaging actions. So for 10 current upcoming targets that are within line of sight, you also get the charging, DSAT, and downlink actions. Then the reward function, compared to the previous paper, which just looked at imaging reward and didn't care about any balancing. Now we have a component that is for the imaging aspect of the problem, and another component that is alpha tuned that is for the downlink component. So meaning we want to actually have all the illuminated images on the ground. So the imaging component is that you need to pass all the criteria for imaging, which means that your illumination factor needs to be above the threshold, the line of sight needs to be maintained by the time that you slew to it, and there's pointing and pointing rate constraints as well, and then you get the priority of the target times 1 minus alpha. On the other side, the downlink, you only get points if you actually downlink a illuminated image, meaning a successful image. So if you take an image where the satellite was no longer illuminated but was actually dark, you still store data in the buffer, so that needs to be removed, and you don't get any points for that. But you do get points if you downlink a successful an illuminated image. In terms of the transition function, we're using Basilisk as our deterministic transition, so we're propagating in that simulator. The step duration delta t varies depending on which action you're choosing, and the terminal state includes the empty battery, so if the battery dies or if the reaction wheel speeds is exceeded, or you actually image all the 100 targets in the time frame. So looking into the results, first, the robustness of LEO train policy in a mixed environment where you have LEO, MEO, and GEO targets. Looking straight into the results here, in particular these first 3 columns, the total reward is actually higher when you go from a LEO environment to a mixed environment. And here we're using a policy of alpha equals 0.5. So you get half the points for imaging a satellite, imaging an RSO, and the other half for downlinking it. So here we do see that the performance is actually increasing in terms of illuminated images as well as downlinked images. And that is because of a couple of main reasons here, which is that MEO and GEO targets are actually easier to image because they have shorter eclipse durations and they're also longer in terms of visibility windows. So there's an easier opportunity to actually image them. Interestingly, however, is that despite the distribution being 50, 30, 20 across the environment in terms of LEO, MEO, GEO populations, the mixed environment, when trained using a LEO trained policy, is still preferring slightly LEO targets and GEO targets in the correct amounts. LEO targets in a higher amount and MEO targets in a lower amount compared to what they are represented in the sample. Overall, though, improved performance in the environment is achieved using a zero-shot transfer, which is quite interesting. So you don't need to train in one environment to use it in another, at least in the combinations that we have done here. Trade-off between imaging and downlink reward. In this alpha study, we're looking at reward, illuminated images, and downlink images. As we can see, the total reward is higher for lower alphas, which does make sense because the task is essentially easier. So in this case, for lower alphas, we are only required to really image to get all the reward. We downlink less frequently because that's not as important. If we actually are prioritizing downlinked images, we have to do 2 actions. We first have to image and we have to downlink to actually essentially get the reward, which meaning that that's a more difficult task. And therefore, our reward actually goes down with higher alphas. The largest amount of downlinked images, interestingly, also doesn't happen at alpha 1.0, but actually somewhat before at alpha 0.3 or 0.4. And if we look at alpha 0, that number of downlinked images is down here about 80. If we look at this in a bit more detail. If we look at the action count here, the downlink actions is the downward arrow here on the bottom. It actually increases up to a level of 0.5 alpha and then starts to plateau. The imaging actions does the reverse behavior here. If we actually see how those downlinked images are actually being sent to the ground, here there is quite a difference. So downlinked images is similar for any alpha that's higher than 0 with a slight downward trend, but the way that they're downlinked is different. If we look at alpha 0.1, in that scenario, we're downlinking about a third of the mean downlink fraction. So a third of the buffer is being emptied every time we have a successful downlink. Whereas if you look at the alpha 1.0 solution, which gets slightly less downlinked images overall, it does so by emptying every time around a half of a third, so around 0.17 or so. And this indicates kind of we see this indicative trend here, and this indicates that you actually get less downlinked images on the ground, but at a higher rate. So it might be more interesting to operators on the ground, even though you get slightly less overall. If we now look at the trade-off between downlink and imaging when we're looking at this particular case study, it also shows the difference. So in alpha equals 0 solution policy, here we're only downlinking twice, and in particular only once we get to close to full storage, and we don't get many downlinked images on the ground at the end, especially when comparing to this alpha 0.1 solution, which downlinks quite a bit more frequently and achieves a higher number of downlinked images and a higher number of illuminated images on board. And if we push this even further, here we're using alpha 1.0. This is the most extreme case where the reinforcement learning agent is only getting rewarded when it's downlinking an illuminated image. Here we can see it's really trying to use every single ground station window that it has to downlink whatever data it has on the ground, whatever data it has to the ground. It does result in slightly less illuminated images on board, as well as also two critical battery level stages where the shield had to interact and intervene and charge. And we do see that downlinking is done sometimes less efficiently because it's trying to really force it with many downlink actions iteratively. However, it does bring basically the lowest ground delivery time because you're using every possible ground station window. Lastly, I want to look at eclipse imaging analysis, so understanding what is the agent doing when it's in particular a bad or difficult spot, which is when the spacecraft itself is in eclipse and most of the other spacecrafts around it might also be in eclipse. So here we try to make a metric, which is an eclipse effectiveness metric. So if the agent is selecting an illuminated target, that's already something good. Secondly, if it is selecting a higher altitude target like a MEO or GEO satellite, which is more likely to remain illuminated, that's also something that is a good behavior. And lastly, it's also eclipse effective behavior if you're selecting a sunward biased LEO target. So one that, if you look at an eclipse, it's not exactly even between how deep the eclipse is on one side or the other. So if it is choosing towards the sun, those are the LEO targets that will remain in illuminated or are less likely to get into the eclipse as they are being imaged. Out of the 150 actions that you have around when you're doing 8 orbits here, 41 of those are in those eclipse periods, and 37 of those would classify as eclipse effective behavior, which really shows that the RL policy is learning physical reasoning, which is something really interesting, and doing something that would be perhaps hard to do with a heuristic method. Overall, to conclude, we've demonstrated that RL policies trained to handle LEO to LEO imaging can also successfully be used to a mixed regime environment. Secondly, imaging downlink trade-offs can be achieved by tuning multi-objective reward functions, and you can really understand and differ the behavior of the way you're sending images to the ground by changing with the alpha And lastly, we saw that RL policies really learn effective eclipse-aware behavior that aim to take actions with higher likelihood of leading to a successful image. Overall, RL applied to space-based sensor tasking shows it can support real-time onboard autonomy for mixed regime space situational awareness. In future work, what we want to do is re-image targets so we really are maintaining a catalog over time, and also relax the assumption of a fixed imaging constraint, such that we can kind of switch faster between having one image done to the next. And lastly, we want to expand this scenario to multi-agents where we have various satellites working in tandem to maintain a catalog together. Thank you very much.